There is a planet 120 light years from Earth that may have life on it, not might have had life billions of years ago, not might have microbial life in some deep subsurface environment where we could never detect it. Life right now in its oceans, producing a chemical that in every known instance in the universe is produced by living organisms and only by living organisms. The planet is called K2-18b. The chemical is called dimethyl sulfide, and the telescope that detected the signal was James Webb. I want to be honest with you about what has been detected and what has not, because this topic sits at the intersection of extraordinary scientific possibility and the very human tendency to hear what we want to hear. The detection of dimethyl sulfide in the atmosphere of K2-18b is real. It was published in a peer-reviewed journal by a team of serious scientists at Cambridge University, led by the astrophysicist Nikku Madhusudhan. The statistical significance of the detection is approximately 3 sigma, which in particle physics terms is considered a hint or a candidate rather than a confirmed discovery. 5 sigma is the threshold for discovery in the physical sciences. 3 sigma means the probability of the signal being a random fluctuation is about 1 in 370. That is not nothing. That is not confirmation. But here is what makes this specific detection different from the hundreds of astronomical anomalies that are reported and forgotten every year. The specific combination of molecules detected in K2-18b's atmosphere is not just individually interesting. The combination taken together has no known explanation that does not involve biology. Carbon dioxide and methane are both present. Carbon monoxide is absent at the level it would be expected if the chemistry were purely abiotic. And dimethyl sulfide, a molecule with no known significant abiotic production pathway in planetary atmospheres, is present at a level that, if confirmed, would require something to be actively making it. In the context of astrobiology and the search for biosignatures, this is the most significant detection that any instrument has ever made. Not confirmed, not proven. But more specific, more quantitatively grounded, and more difficult to explain without biology than anything that has come before it. And the scientists who made the detection are trying very hard, in the careful language of peer-reviewed science, not to say the thing that the data is pointing toward, because saying it before the statistics reach 5 sigma, before the alternative explanations have been exhaustively ruled out, before independent observations by other instruments have confirmed the signal, would be scientifically irresponsible. I think you deserve to understand the full picture, not the cautious version and not the breathless version. The honest version, with all its uncertainty and all its potential significance laid out as clearly as physics and chemistry can lay them out. Let me start with the planet itself, because K2-18b is interesting independent of the biosignature question, and understanding what kind of world it is essential for understanding why the detection matters. K2-18. B was discovered in 2015 by the Kepler Space Telescope's K2 mission, which was the second phase of the Kepler mission after the original telescope's primary pointing capability was lost. Kepler detected K2-18b by the transit method, observing the tiny dimming of the host star's light as the planet passed in front of it. The transit method gives 2 pieces of information directly: the size of the planet relative to the star from the depth of the dimming, and the orbital period from the timing of successive transits. K2-18b has a radius approximately 2.6 times that of Earth and a mass approximately 8.6 times that of Earth. This combination of radius and mass puts it in a category of planet called a sub-Neptune, or a Hycean world, a planet too large and too low density to be a rocky world like Earth or Mars, but too small and too dense to be a gas giant like Jupiter or Neptune. Planets in this size range were not known to exist until the Kepler mission began revealing the true diversity of planetary sizes in the galaxy. They have no analog in our solar system. The physics of their interiors and atmospheres is not as well understood as the physics of rocky planets or gas giants. And this uncertainty is relevant to the biosignature question in ways I will come back to. K2-18b orbits a red dwarf star, K2-18, at a distance that places it in the star's habitable zone, the region where the temperature would allow liquid water on the surface of a planet with a suitable atmosphere. Red dwarf stars are cooler and dimmer than the Sun, and their habitable zones are much closer to the star than the habitable zone of a Sun-like star. K2-18b orbits at a distance of about 0.14 astronomical units, roughly 1/7 the distance from Earth to the Sun, with an orbital period of about 33 days. Despite this close orbit, the cooler red dwarf produces a flux of energy at K2-18b's orbital distance that is comparable to what Earth receives from the Sunday. Let me start with the planet itself, because K2-18b is interesting independent of the biosignature question, and understanding what kind of world it is essential for understanding why the detection matters. K2-18b was discovered in 2015 by the Kepler Space Telescope's K2 mission, which was the second phase of the Kepler mission after the original telescope's primary pointing capability was lost. Kepler detected K2-18b by the transit method, observing the tiny dimming of the host star's light as the planet passed in front of it. The transit method gives two pieces of information directly: the size of the planet relative to the star from the depth of the dimming, and the orbital period from the timing of successive transits. K2-18b has a radius approximately 2.6 times that of Earth and a mass approximately 8.6 times that of Earth. This combination of radius and mass puts it in a category of planet called a sub-Neptune, or a Hycean world, a planet too large and too low density to be a rocky world like Earth or Mars, but too small and too dense to be a gas giant like Jupiter or Neptune. The term Hycean, coined by Nikku Madhusudhan and his collaborators in a 2021 paper, stands for hydrogen ocean. It describes a specific type of sub-Neptune in which a thick hydrogen-rich atmosphere sits above a global ocean of liquid water. The atmospheric pressure at the ocean surface would be much higher than on Earth, and the temperature of the ocean would be higher than Earth's surface temperature, despite being in the star's habitable zone because of the greenhouse effect of the thick hydrogen atmosphere. But the conditions in the ocean, pressure and temperature, might be within the range that life can tolerate. Certain extremophile organisms on Earth survive pressures similar to what would be found in a shallow Hycean ocean, and the elevated temperatures, while higher than typical Earth surface temperatures, are within the range that thermophilic organisms can survive. The Hycean world concept is important for astrobiology for a specific reason. Sub-Neptunes in the relevant size range, roughly 1.5 to 2.5 Earth radii, are the most common type of planet in the galaxy, according to the Kepler statistics. They significantly outnumber rocky Earth-like planets. If Hycean worlds can support life, the potential habitats for life in the galaxy are far more numerous than if only rocky planets with thin atmospheres like Earth can support it. Whether a given sub-Neptune in the habitable zone is actually a Hycean world rather than a mini-Neptune with a thick, hot, uninhabitable atmosphere depends on specific details of its internal structure and composition. The mass and radius of K2-18b are consistent with a Hycean world model, but they are also consistent with other internal structures. Distinguishing between these possibilities through one atmospheric characterization, which is exactly what James Webb provides. K2-18 B orbits a red dwarf star, K2-18, at a distance that places it in the star's habitable zone. K2-18 is an M2-5 dwarf, a relatively cool red dwarf with a surface temperature of approximately 3,400 Kelvin compared to the Sun's 5,778 Kelvin. The star is about 0.36 solar masses and about 0.41 solar radii, K2-18. B orbits at a distance of about 0.14 astronomical units with an orbital period of about 33 days. One important characteristic of K2-18 relevant to astrobiology is its level of stellar activity. Red dwarfs can be very active, producing frequent flares that bombard their close-in planets with ultraviolet and X-ray radiation. K2-18 is a relatively quiet red dwarf, less active than many of its type, which reduces one of the main concerns about habitability around red dwarfs. The lower flare rate means less bombardment of K2-18b's atmosphere with harmful radiation, reducing the rate at which the atmosphere is eroded and reducing the flux of UV reaching the ocean surface. K2-18b is also known to have a companion, a smaller planet called K2-18c, which orbits closer to the star with a period of about 9 days. The existence of the companion is relevant because it tells us something about the planetary system architecture, but K2-18c is unlikely to be in the habitable zone. The distance from Earth to K2-18 is approximately 120 light years. This is far enough that we cannot image the planet directly with any current telescope, but it is close enough that the light from the host star filtered through K2-18b's atmosphere during transits carries detectable spectroscopic signatures of the atmospheric chemistry. This is transmission spectroscopy, one of the primary tools of exoplanet atmosphere characterization, and it is where James Webb comes in. When a planet transits its host star, a fraction of the starlight passes through the planet's atmosphere before reaching us. The atmosphere absorbs some of the light at specific wavelengths determined by the molecular composition of the atmosphere. Different molecules absorb at different wavelengths. Water absorbs at certain infrared wavelengths, carbon dioxide at others, methane at others, and so on. By comparing the spectrum of the star when the planet is transiting to the spectrum when it is not, astronomers can identify the molecules present in the planet's atmosphere, at least those that are present in sufficient quantities to produce detectable absorption. This technique was pioneered with the Hubble Space Telescope and Spitzer Space Telescope, but both instruments had significant limitations in sensitivity and wavelength coverage. James Webb has a much larger mirror, 6.5 meters in diameter compared to Hubble's 2.4 meters, and observes in the infrared at wavelengths that are optimal for detecting the molecular absorption features of many biologically relevant gases. It has fundamentally transformed the field of exoplanet atmosphere characterization since beginning science operations in 2022. The Cambridge team led by Madhusudhan used James Webb to observe K2-18b during multiple transits. They combined the James Webb data with earlier Hubble observations to produce a comprehensive spectrum of K2-18b's atmosphere, spanning a wide range of infrared wavelengths. When a planet transits its host star, a fraction of the starlight passes through the planet's atmosphere before reaching us. The atmosphere absorbs some of the light at specific wavelengths determined by the molecular composition of the atmosphere. Different molecules absorb at different wavelengths. Water absorbs at certain infrared wavelengths, carbon dioxide at others, methane at others, and so on. By comparing the spectrum of the star when the planet is transiting to the spectrum when it is not, astronomers can identify the molecules present in the planet's atmosphere, at least those that are present in sufficient quantities to produce detectable absorption. Let me explain the physics of this in more detail, because it helps to understand why James Webb is so powerful for this type of observation. Every molecule has a specific set of quantum mechanical energy levels determined by the masses of its atoms and the chemical bonds between them. When a photon of the right energy hits a molecule, it can be absorbed, exciting the molecule from a lower energy level to a higher one. The energy of the photon corresponds to a specific wavelength of light according to Planck's relation E equals hf, where f is frequency. Different molecules have different sets of energy levels and therefore absorb at different wavelengths. For molecules with multiple atoms, there are many types of energy levels: electronic levels, vibrational levels, and rotational levels. The vibrational and rotational transitions of molecules typically produce absorption features in the infrared at wavelengths longer than visible light. The specific pattern of absorption features, the specific wavelengths at which a molecule absorbs, is like a fingerprint. No two molecules have the same pattern of vibrational and rotational absorption features. By identifying the absorption features in a planetary atmosphere spectrum, we can determine which molecules are present. James Webb's near-infrared and mid-infrared instruments cover the wavelength range from about 0.6 to 28 microns. This range includes the absorption features of a wide variety of molecules relevant to planetary atmospheres and to life: water, carbon dioxide, carbon monoxide, methane, ammonia, nitrous oxide, and others including dimethyl sulfide. The large mirror of James Webb collects vastly more photons than any previous space telescope, making it possible to achieve the signal-to-noise ratio needed to detect weak absorption features in planetary atmospheres. For K2-18b, the transmission spectroscopy works as follows. During the roughly 3 hours when K2-18b is transiting K2-18, James Webb collects light from the star. Some of this light has passed through the planet's atmosphere. The rest has passed to the side of the planet or directly over it. By comparing the spectrum during transit to the spectrum outside transit, the team extracts the atmospheric transmission spectrum, the ratio of the in-transit to out-of-transit spectra, which shows the wavelengths at which the atmosphere is absorbing starlight. The extraction of the atmospheric signal requires careful handling of numerous systematic effects. The star itself has features in its spectrum that can mimic or mask planetary atmospheric features. The instruments have wavelength-dependent sensitivities that must be calibrated. The planet's motion across the face of the star during the transit introduces Doppler shifts that must be accounted for. Stellar activity, including star spots and faculae, can change the star's spectrum in ways that contaminate the atmospheric signal. The analysis team must model all of these effects and subtract them to isolate the planetary atmospheric signal. The Cambridge team collected data from 2 transits of K2-18b with James Webb's NIRISS instrument and 2 transits with James Webb's NIRSpec G 395H instrument, together covering a wavelength range from about 1 to 5.2 microns. They combined this with earlier Hubble data to extend the wavelength coverage. The combined data set represents the most comprehensive spectroscopic characterization of K2-18b's atmosphere yet obtained. The analysis of this spectrum revealed the presence of several molecules: carbon dioxide, methane, and, at lower statistical significance, dimethyl sulfide. The carbon dioxide and methane detections were expected for a Hycean world with a hydrogen-rich atmosphere. These molecules are common in planetary atmospheres, and their presence tells us about the temperature, pressure, and general chemical state of the atmosphere. The dimethyl sulfide detection was not expected. Dimethyl sulfide, with the chemical formula CH3, SCH3, is an organic sulfur compound. On Earth, it is produced primarily by marine phytoplankton. the microscopic photosynthetic organisms that form the base of the ocean food chain. When phytoplankton break down dimethylsulfonopropionate, a compound they produce to regulate osmotic pressure in their cells, they release dimethyl sulfide. The dimethyl sulfide diffuses into the atmosphere, where it plays an important role in cloud formation over the oceans. It is one of the primary sources of sulfur in the marine atmosphere, and its distinctive smell is largely responsible for what people describe as the smell of the sea. The relevant fact for astrobiology is that dimethyl sulfide on Earth is produced almost entirely by living organisms. It has no significant known abiotic production pathway in planetary atmospheres. It is not produced by volcanic activity in significant quantities. It is not produced by photochemistry in significant quantities. It is not produced by lightning or cosmic ray interactions in significant quantities. Every significant source of dimethyl sulfide in Earth's atmosphere is biological. The relevant fact for astrobiology is that dimethyl sulfide on Earth is produced almost entirely by living organisms. It has no significant known abiotic production pathway in planetary atmospheres. It is not produced by volcanic activity in significant quantities. It is not produced by photochemistry in significant quantities. It is not produced by lightning or cosmic ray interactions in significant quantities. Every significant source of dimethyl sulfide in Earth's atmosphere is biological. Let me be more specific about the biochemistry, because I think it illuminates why dimethyl sulfide is such a specific biosignature. Marine phytoplankton synthesize an organic compound called dimethylsulfonopropionate, or DMSP, as an osmolyte, a molecule that helps regulate the salt concentration inside their cells. When phytoplankton die, are grazed by zooplankton, or are attacked by viruses, the DMSP is released into the water, where it is broken down by bacteria into dimethyl sulfide and acrylate. The dimethyl sulfide then diffuses from the ocean surface into the atmosphere. In the atmosphere, it reacts with hydroxyl radicals and other oxidants, producing sulfate aerosols that serve as cloud condensation nuclei, helping to seed the formation of clouds over the ocean. This role of dimethyl sulfide in cloud formation was identified by Robert Charlson, James Lovelock, Meinrad Andrié, and Stephen Warren in a 1987 paper that proposed the claw hypothesis, the idea that phytoplankton regulate Earth's climate in part by controlling the dimethyl sulfide flux into the atmosphere. The claw hypothesis remains influential, though the details of the climate feedback have been revised in subsequent research. The key point for astrobiology is the pathway. Dimethyl sulfide comes from DMSP, which comes from phytoplankton, which are living organisms. The production of DMSP is a specific biochemical adaptation, the use of a sulfur-containing organic molecule as an osmolyte that evolved in marine organisms as a response to the challenge of living in a high salt environment. It is a specific biological invention, not a generic chemical reaction. Could life on K2-18b have independently invented something like DMSP biochemistry? If K2-18b has a global ocean, and if that ocean contains organisms with cell membranes that need osmotic regulation, the development of DMSP or a similar organic osmolyte would make biological sense. Whether the specific molecule would be dimethylsulfonopropionate or something else, and whether its breakdown product would be dimethyl sulfide or a different compound, depends on the specific biochemistry that evolved. But the general principle that oceanic organisms in a high-pressure, high-salt environment might evolve sulfur-based osmolytes whose breakdown produces atmospheric sulfur compounds is biologically reasonable. This does not mean dimethyl sulfide can only be produced by life. It means that we do not currently know of any abiotic process that produces it in significant quantities. The most important caveat is that K2-18b is a very different kind of world from Earth. It is a Hycean world, a sub-Neptune with a hydrogen-rich atmosphere and, potentially, a deep global ocean of water. The chemistry of a hydrogen-rich atmosphere at the temperatures and pressures relevant to K2-18b is different from the chemistry of Earth's nitrogen-oxygen atmosphere. There may be chemical reactions in hydrogen-rich atmospheres that produce dimethyl sulfide abiotically at rates that would be negligible in Earth's atmosphere but significant in a hydrogen-rich one. This is a serious possibility that the Cambridge team acknowledges, and it is one of the main reasons the community has been cautious about the interpretation. A specific abiotic pathway that has been discussed is the reaction of methane and hydrogen sulfide under ultraviolet irradiation in a hydrogen-rich atmosphere. This reaction has been shown to produce dimethyl sulfide and related compounds in laboratory experiments, though the rates and the specific conditions required are not well characterized for the specific atmospheric conditions of K2-18b. More laboratory work and more detailed photochemical modeling of K2-18b's atmosphere are needed before this pathway can be definitively ruled in or out. Another caveat is the statistical significance. 3 sigma is a real detection in the sense that the signal is probably not a statistical fluctuation. But 3 sigma is not 5 sigma, and the history of astronomy contains many 3 sigma detections that faded away when more data was collected. The dimethyl sulfide signal needs to be confirmed by additional observations, ideally using different observing modes and different instruments before it can be considered reliable. There is also the question of systematic errors. Transmission spectroscopy of exoplanet atmospheres is technically demanding, and the analysis involves many steps where errors can be introduced. The stellar spectrum must be carefully subtracted to isolate the planetary atmospheric signal. The instrument calibration must be accurate. The modeling of the atmospheric absorption must correctly account for all the relevant physics and chemistry. The Cambridge team has been careful in their analysis, but independent analyses by other groups have produced somewhat different results, with some finding weaker evidence for dimethyl sulfide than the Cambridge team reported. With all these caveats stated honestly and completely, let me tell you why I think this detection is still scientifically significant and why it deserves serious attention even at 3 sigma. The significance is not in the dimethyl sulfide detection alone. It is in the combination of molecular detections and the absence of specific molecules that together form a pattern. Carbon dioxide and methane are both present. This is interesting because, as I mentioned earlier, carbon dioxide and methane react with each other in the absence of a continuous source. In an abiotic atmosphere, if both are present, the reaction between them would gradually consume one or both over geological timescales. The simultaneous presence of both at detectable levels without being completely depleted suggests either a continuous source replenishing both or specific chemical conditions that inhibit the reaction. On Earth, the continuous source of both carbon dioxide and methane in the atmosphere is biology. Plants and ocean chemistry regulate carbon dioxide. Bacteria, wetlands, and animals regulate methane. Without biology, both gases would reach a chemical equilibrium that is very different from what we observe. The simultaneous presence of both at specific levels is a biological signature precisely because biology is what maintains them both in a state that is far from chemical equilibrium. The absence of carbon monoxide is also significant. In a hydrogen-rich atmosphere at K2-18b's temperature, abiotic chemistry should produce substantial carbon monoxide from the reactions between carbon dioxide, methane, and hydrogen. The observed level of carbon monoxide in K2-18b's atmosphere is lower than abiotic chemistry predicts. The most natural explanation for the low carbon monoxide is that something is consuming it, converting it to other compounds. On Earth, certain types of bacteria metabolize carbon monoxide as an energy source. In a Hycean ocean, biological carbon monoxide consumption could maintain the atmospheric level below the abiotic prediction. None of this proves life. Each of these features has potential abiotic explanations. But the combination, dimethyl sulfide present, methane and carbon dioxide both present, carbon monoxide depleted below abiotic predictions, forms a pattern that is consistent with biology and inconsistent with the simplest abiotic models of K2-18b's atmospheric chemistry. Nikku Madhusudhan, the leader of the Cambridge team, has described K2-18b as a candidate Hycean world with a potential biosignature. This careful language reflects genuine scientific caution. He is not claiming detection of life. He is identifying K2-18b as a priority target for follow-up observations and as a world where the atmospheric chemistry is intriguing enough to warrant serious scientific attention. Now let me put this detection in the broader context of the search for biosignatures, because I think understanding the full history and the full landscape of the search helps calibrate the significance of what James Webb has found. The search for biosignatures, chemical or physical signs of life in planetary atmospheres observable from a distance, has a long theoretical history but a short observational history. The concept of using spectroscopic observations to search for life on other planets was developed seriously in the 1990s, when Earth-observing satellites and the development of the Hubble Space Telescope created the theoretical and practical foundation for what would eventually become exoplanet atmosphere characterization. The key theoretical insight, developed by James Lovelock and later elaborated by Carl Sagan and others, is that life fundamentally perturbs the chemistry of a planetary atmosphere. Life takes chemical energy from the environment and uses it to maintain a thermodynamically improbable state itself. In doing so, it leaves chemical signatures in the atmosphere that reflect this thermodynamic imbalance. An atmosphere in chemical equilibrium with no life will tend towards specific compositions determined by the temperature, pressure, and chemical composition of the planet's crust and interior. An atmosphere with life will be maintained in a state far from that equilibrium, with specific molecules present at levels that can only be maintained by continuous biological production. The most obvious signature of life on Earth, to a distant observer, is the simultaneous presence of large amounts of oxygen and methane in the atmosphere. Oxygen and methane react spontaneously with each other. In the absence of a continuous source of both, they would quickly consume each other, and the atmosphere would reach a lower energy equilibrium with much less wrong of both. The fact that Earth's atmosphere contains both at substantial concentrations is the result of biology. Photosynthesis produces the oxygen, and methanogenic bacteria produce the methane. No known abiotic process can maintain both at the levels observed on Earth. Oxygen alone is not a biosignature because abiotic photochemistry can produce oxygen through the photolysis of water or carbon dioxide. But oxygen in combination with methane is a much stronger biosignature because maintaining both simultaneously requires specific biological processes. The search for biosignatures, chemical or physical signs of life in planetary atmospheres observable from a distance, has a long theoretical history but a short observational history. The concept of using spectroscopic observations to search for life on other planets was developed seriously in the 1990s, when Earth-observing satellites and the development of the Hubble Space Telescope created the theoretical and practical foundation for what would eventually become exoplanet atmosphere characterization. The key theoretical insight, developed by James Lovelock and later elaborated by Carl Sagan and others, is that life fundamentally perturbs the chemistry of a planetary atmosphere. Life takes chemical energy from the environment and uses it to maintain a thermodynamically improbable state itself. In doing so, it leaves chemical signatures in the atmosphere that reflect this thermodynamic imbalance. An atmosphere in chemical equilibrium with no life will tend towards specific compositions determined by the temperature, pressure, and chemical composition of the planet's crust and interior. An atmosphere with life will be maintained in a state far from that equilibrium, with specific molecules present at levels that can only be maintained by continuous biological production. The most obvious signature of life on Earth, to a distant observer, is the simultaneous presence of large amounts of oxygen and methane in the atmosphere. Oxygen and methane react spontaneously with each other. In the absence of a continuous source of both, they would quickly consume each other, and the atmosphere would reach a lower energy equilibrium with much less of both. The fact that Earth's atmosphere contains both at substantial concentrations is the result of biology. Photosynthesis produces the oxygen, and methanogenic bacteria produce the methane. No known abiotic process can maintain both at the levels observed on Earth. The theoretical foundation of biosignature science has been developed into a formal framework by researchers, including Sarah Seeger at MIT, who has been one of the most influential voices in the field. Seeger's work has focused on identifying which combinations of molecules would constitute the most compelling biosignatures in different planetary environments, developing what she calls a biosignature scorecard that takes into account not just the presence of a given molecule, but the abundance of that molecule relative to what abiotic chemistry would produce, the presence of co-occurring molecules that support a biological interpretation, and the absence of molecules that abiotic chemistry would predict. On K2-18b, the relevant molecules are not oxygen and methane, but carbon dioxide, methane, and dimethyl sulfide. The logic is analogous. The specific combination detected is more consistent with a living ocean chemistry than with abiotic chemistry, and the presence of dimethyl sulfide in particular has no compelling abiotic explanation. Before the James Webb era, the best atmospheric characterization of an exoplanet had been achieved with Hubble and Spitzer on a handful of hot Jupiters, gas giants, orbiting extremely close to their stars. These observations revealed the presence of water vapor and other molecules in hot Jupiter atmospheres, demonstrating that transmission spectroscopy was feasible but not yet sensitive enough to detect the weak signals expected from smaller, cooler, more Earth-like planets. James Webb changed this. Its first year of exoplanet atmosphere science produced results that were qualitatively better than anything Hubble had achieved. The WASP 39b observations I mentioned in the James Webb cosmology video demonstrated that Webb could detect specific molecules at levels not previously achievable from space. K2-18b was one of the first Hycean world candidates to be observed by Webb, and the results have been the most discussed in the astrobiology community. The most obvious signature of life on Earth to a distant observer is the simultaneous presence of large amounts of oxygen and methane in the atmosphere. Oxygen alone is not a biosignature because abiotic photochemistry can produce oxygen through the photolysis of water or carbon dioxide. But oxygen, in combination with methane, is a much stronger biosignature because maintaining both simultaneously requires specific biological processes. For K2-18b, the biosignature logic is similar but different in its specifics, because the atmospheric composition is fundamentally different from Earth's. The relevant chemical reactions are different. The relevant abiotic and biotic processes are different. And the interpretation of any given molecular detection requires understanding the specific chemistry of a hydrogen-rich atmosphere over a water ocean. The dimethyl sulfide detection is compelling in the K2-18b context precisely because dimethyl sulfide is such a specific indicator of biological activity on Earth. Unlike oxygen or methane, which have known abiotic sources, dimethyl sulfide's primary production on Earth is almost entirely biological. Its detection in a planetary atmosphere is therefore a stronger biosignature candidate than many other molecules. But the K2-18b detection is also compelling because it was not what the team was specifically looking for. The original goal of the James Webb observations was to characterize the general atmospheric composition, searching for the water, carbon dioxide, and methane expected in a hydrogen-rich atmosphere. The dimethyl sulfide detection emerged from the data analysis as an additional, unexpected feature. Unexpected detections that survive rigorous analysis are often the most significant because they are not susceptible to the confirmation bias that can affect searches for specific signals. Let me now discuss the alternative explanations for the dimethyl sulfide signal in more detail, because I think honest engagement with these alternatives is essential, and because the alternatives are themselves scientifically interesting. The first alternative, as I mentioned, is abiotic photochemistry in a hydrogen-rich atmosphere. The specific concern is that ultraviolet photons from K2-18, the host red dwarf star, might drive reactions between methane, hydrogen sulfide, and other sulfur-containing compounds in the upper atmosphere that produce dimethyl sulfide. Red dwarf stars are cooler than the sun and produce less ultraviolet radiation, but they are also more prone to flares, intense bursts of radiation that can temporarily dramatically increase the ultraviolet flux at the planet's surface. The photochemistry of hydrogen-rich atmospheres under variable ultraviolet irradiation from red dwarf stars is an active area of research, and the community does not yet have a complete understanding of what molecules might be produced in such environments. Several research groups have begun modeling the photochemistry of K2-18b's atmosphere in detail, attempting to calculate the expected atmospheric composition from first principles and compare it to the James Webb observations. This work is ongoing, and preliminary results suggest that while some abiotic production of dimethyl sulfide might occur, the levels predicted by current abiotic models are substantially lower than what was detected, but the models are not complete, and until they are, the abiotic possibility remains open. The second alternative is that the dimethyl sulfide signal is instrumental, a systematic error in the James Webb data or the analysis. This possibility is taken seriously by the community, particularly because the dimethyl sulfide absorption features overlap with absorption features of other molecules in the same wavelength range, making the spectral deconvolution challenging. Independent analyses of the same data have produced slightly different conclusions, with some finding weaker evidence for dimethyl sulfide. This disagreement among independent analyses is itself informative. It suggests that the signal is at the edge of detectability with the current data, and that the interpretation depends sensitively on the assumptions made in the analysis. The third alternative is that K2-18b is a mini Neptune rather than a Hycean world, with a dense, hot interior rather than a surface ocean. If the planet has no ocean, the chemistry of its atmosphere would be very different from the Hycean model, and the interpretation of the molecular detections would change significantly. The distinction between Hycean worlds and mini Neptunes with thick atmospheres is an active area of research, and the mass and radius of K2-18b are consistent with both types. These alternatives are real, and they need to be addressed before any confident claim about K2-18b can be made. The scientific process is working as it should. A potentially significant detection has been made, the team has published it with appropriate caveats, and the community is now engaged in the work of testing, replicating, and refuting or confirming the finding. What will it take to resolve the question? More James Webb observations are clearly needed, and the team has already been allocated additional observing time. More transits observed with James Webb will improve the signal-to-noise ratio and make the detection either more robust or reveal it as an artifact. Different observing modes, including emission spectroscopy, which observes the thermal emission from the planet's day side rather than the transmission through its atmosphere, can provide complementary information about the atmospheric composition. The upcoming extremely large telescope in Chile, currently under construction, will have the sensitivity to characterize K2-18b's atmosphere in greater detail than James Webb, providing an independent confirmation or refutation of the Webb findings. The Ariel mission, a European Space Agency mission designed specifically for exoplanet atmosphere characterization, will be launched in 2029 and will be able to observe K2-18b in detail. The broader context matters too. K2-18b is not the only Hycean world candidate. There are several others within the range accessible to James Webb. If the dimethyl sulfide detection on K2-18b is real and biological, we might expect to find similar signatures on other Hycean worlds if life is widespread, or not find them on similar worlds if K2-18b is unique. The statistics of biosignature detections across a population of similar worlds will be the most powerful evidence one way or another. What will it take to resolve the question? More James Webb observations are clearly needed, and the team has already been allocated additional observing time. More transits observed with James Webb will improve the signal-to-noise ratio and make the detection either more robust or reveal it as an artifact. Different observing modes, including emission spectroscopy, which observes the thermal emission from the planet's day side rather than the transmission through its atmosphere, can provide complementary information about the atmospheric composition and temperature structure. Emission spectroscopy is particularly valuable because it probes different parts of the atmosphere than transmission spectroscopy. Transmission spectroscopy is sensitive to the composition of the atmosphere at the terminator, the day-night boundary, at specific pressure levels. Emission spectroscopy probes the day-side atmosphere at different pressure levels. If the dimethyl sulfide signal is real and biological, it should be present in both the transmission and emission spectra. If it is an artifact of the transmission analysis, it may not appear in emission. The upcoming extremely large telescope in Chile, currently under construction and expected to see first light in the late 2020s, will have the sensitivity to characterize K2-18b's atmosphere in greater detail than James Webb. Its 39-meter primary mirror will collect more than 30 times as many photons as James Webb in the same observing time, enabling much higher signal-to-noise measurements. The ELT's METIS instrument, designed for mid-infrared spectroscopy, will be able to detect dimethyl sulfide and other biosignature molecules at much lower abundance than is currently detectable. The Ariel mission, a European Space Agency mission designed specifically for exoplanet atmosphere characterization, will be launched in 2029 and will observe hundreds of exoplanets, including K2-18b, in a systematic survey. While Ariel is less sensitive than James Webb for any individual target, it will observe many more planets and provide the statistical context needed to understand how common or unusual K2-18b's atmospheric chemistry is. The broader context matters too. K2-18b is not the only Hycean world candidate. There are several others within the range accessible to James Webb, including TOI-270d, a sub-Neptune at roughly 73 light-years, and several others identified by the TESS mission. If the dimethyl sulfide detection on K2-18b is real and biological, we might expect to find similar signatures on other Hycean worlds if life is widespread in the universe. A statistical pattern of biosignature detections across multiple similar worlds would be far more convincing than any single detection, however significant. The development of new theoretical tools is also important. The photochemical models needed to predict what molecules should be present in K2-18b's atmosphere are still being developed and refined. The laboratory measurements of the absorption cross-sections of dimethyl sulfide and other molecules at the temperatures and pressures relevant to Hycean atmospheres are not complete. The quantum chemistry calculations needed to predict the spectroscopic fingerprints of potential biosignature molecules in hydrogen-rich atmospheres are an active area of research. All of this theoretical and laboratory work will sharpen the ability to interpret the observations. I want to say something about the sociology of this discovery, because I think it is revealing about how science works at the frontier. The Cambridge team published their detection in a peer-reviewed journal with statistical caveats and alternative explanations clearly stated. They did not hold a press conference announcing the discovery of life. They wrote a careful scientific paper and made their data publicly available for independent analysis. This is exactly how scientific discoveries at the frontier should be handled. The media response was, predictably, more dramatic than the science warranted. Headlines announced that James Webb had discovered life or found signs of life, using language that the scientists themselves had carefully avoided. This gap between the cautious language of science and the enthusiastic language of science journalism is a recurring feature of astrobiology, a field where the implications of any positive result are so momentous that excitement is inevitable and calibration is difficult. The scientists are trying very hard not to say it. They are right to be careful, but their caution should not be mistaken for uncertainty about whether the signal is there. The signal is there. What is uncertain is what produced it. Now let me take you to what I think is the most important question that the K2-18b detection raises, which is not the question of whether K2-18b has life, important as that is. The most important question is what the detection means for the broader question of whether life is common in the universe. K2-18b orbits a red dwarf star. Red dwarf stars are the most common type of star in the Milky Way, comprising approximately 70 to 75% of all stars. They are much cooler and dimmer than the Sun, living for hundreds of billions to trillions of years, far longer than the current age of the universe. Their habitable zones are close in, but many of them have planets in those habitable zones. The TRAPPIST, one system, 39 light years from Earth, contains 3 planets in the habitable zone of a red dwarf, and all 3 are rocky, Earth-sized worlds. The question of whether life can exist around red dwarfs is one of the most important questions in astrobiology. Red dwarfs present specific challenges for life that Sun-like stars do not. Their close-in habitable zones mean that planets are likely tidally locked, with one face permanently toward the star and one permanently away. This creates extreme temperature gradients that may be incompatible with the existence of a surface ocean unless atmospheric circulation can redistribute heat. Red dwarfs are prone to intense flares that bombard their close-in planets with ultraviolet and X-ray radiation, which can strip planetary atmospheres over geological timescales and can be harmful to surface life. But red dwarfs also have advantages. Their extraordinary longevity means that any life that forms around them has an almost unlimited amount of time to evolve and develop complexity. The universe has not been around long enough for any red dwarf to have died of old age. If life can establish itself around a red dwarf and survive the early challenges, it has billions of years more to explore the possibilities of evolution than life around a Sun-like star. K2-18b, if it has life, would be life around a red dwarf. It would be evidence that life can arise and persist in the habitable zone of the most common type of star in the galaxy, in a planetary type, the Hycean world, that appears to be extremely common in the galaxy based on the Kepler statistics. If life exists there, the implications for the frequency of life in the universe are staggering. K2-18b orbits a red dwarf star. Red dwarf stars are the most common type of star in the Milky Way, comprising approximately 70 to 75% of all stars. They are much cooler and dimmer than the Sun, living for hundreds of billions to trillions of years, far longer than the current age of the universe. Their habitable zones are close in, but many of them have planets in those habitable zones. The TRAPPIST, one system 39 light years from Earth, contains 3 planets in the habitable zone of a red dwarf, and all 3 are rocky, Earth-sized worlds. The question of whether life can exist around red dwarfs is one of the most important questions in astrobiology. Red dwarfs present specific challenges for life that Sun-like stars do not. Their close-in habitable zones mean that planets are likely tidally locked, with one face permanently toward the star and one permanently away. This creates extreme temperature gradients that may be incompatible with the existence of a surface ocean, unless atmospheric circulation can redistribute heat. Red dwarfs are prone to intense flares that bombard their close-in planets with ultraviolet and X-ray radiation, which can strip planetary atmospheres over geological timescales and can be harmful to surface life. The early history of red dwarf stars, their first billion years or so, can be particularly active and damaging for any budding biosphere. For K2-18b specifically, the tidal locking concern is moderated by the fact that K2-18b is a Hycean world with a thick, hydrogen-rich atmosphere. Thick atmospheres are much more efficient at redistributing heat around a planet than thin ones, reducing the temperature difference between the day and night sides. The Hycean Ocean would also act as a heat reservoir, moderating temperature extremes. The specific conditions on K2-18b, with its thick atmosphere and potential global ocean, may mitigate many of the challenges that tidal locking poses for habitability. The flare activity concern is also reduced for K2-18, which is a relatively quiet red dwarf. The ultraviolet flux at K2-18b is lower than at many red dwarf habitable zone planets, which reduces the rate of atmospheric erosion and the UV dose at the ocean's surface. In a deep ocean, life would be even more protected from UV radiation than on a planet's surface. But red dwarfs also have advantages. Their extraordinary longevity means that any life that forms around them has an almost unlimited amount of time to evolve and develop complexity. The universe has not been around long enough for any red dwarf to have died of old age. If life can establish itself around a red dwarf and survive the early challenges, it has billions of years more to explore the possibilities of evolution than life around a sun-like star. The universe currently has many more old red dwarfs than old sun-like stars, simply because red dwarfs live so much longer. If life around red dwarfs is possible, the galaxy is potentially full of ancient, long-lived biospheres with billions of years of evolutionary history. K2-18b, if it has life, would be life around a red dwarf. It would be evidence that life can arise and persist in the habitable zone of the most common type of star in the galaxy, in a planetary type, the Hycean world, that appears to be extremely common in the galaxy based on the Kepler statistics. If life exists there, the implications for the frequency of life in the universe are staggering. This is why the K2-18b detection is being treated with such caution by the scientific community. The stakes are too high to make premature claims. A false positive, a claimed detection of biosignatures that turns out to be abiotic chemistry, would damage the credibility of the field and make it harder to secure resources for the follow-up observations needed to make genuine detections. And the caution itself is a sign of how seriously the detection is being taken. If it were not scientifically significant, the caution would be unnecessary. I want to say something about the relationship between this specific detection and the Fermi paradox that I discussed in the video about the silence of the universe. The Fermi paradox asks why, in a universe apparently filled with habitable planets, we have not detected any sign of other technological civilizations. The K2-18b biosignature, if confirmed, would not resolve the Fermi paradox. It would be evidence of biological life, not of technological civilization. Life and intelligence are very different things. Complex, multicellular, intelligent, technology-developing life has appeared only once in 4 billion years of Earth's history, as far as we know. Even if life is common in the universe, technological civilization may be rare. But the K2-18b biosignature would significantly change the prior probability that life is common. If life has arisen independently in the Hycean ocean of K2-18b, which is a very different environment from the one in which life arose on Earth, then the inference is that life arises whenever and wherever the conditions are suitable in a wide variety of environments and planetary types. And if life is common in the universe, the probability that some of it has developed into technological civilization somewhere, sometime, becomes much larger. The Fermi paradox becomes more acute, not less. A universe in which life is common but technology is rare, in which biology is a widespread phenomenon but intelligence is an extraordinary exception, is a specific and coherent picture of the cosmic distribution of life. It is consistent with the silence of the universe, because simple life does not build radio transmitters or megastructures. It is consistent with the rare Earth hypothesis in a modified form. Perhaps not Earth itself is rare, but the specific sequence of evolutionary steps that led from simple biology to complex intelligent life. And it would make the K2-18b detection the most important scientific result of the 21st century, not because it answers the question of whether we are alone in the universe, but because it changes the answer from maybe to probably not. I want to be honest about where I stand on the K2-18b detection, because I have been developing this picture with considerable care, and I think you deserve my honest assessment. I think the detection is real in the sense that the signal is probably not a statistical fluctuation. The 3 sigma significance is genuine. I think the abiotic alternatives are worth taking seriously and have not been definitively ruled out. I think additional observations will either strengthen the case for biology or reveal an abiotic explanation, and those additional observations are the appropriate scientific response to the current state of the evidence. And I think that even at 3 sigma, even with the caveats and the uncertainties, this is the most scientifically credible candidate biosignature detection that has ever been made. Not because the evidence is conclusive, because the specific combination of molecules detected in a world of this type at this distance forms a pattern that is more consistent with biology than with any specific abiotic alternative that has been proposed. Let me try to convey why this particular moment feels significant to me, even with all the caveats. Throughout my career in physics, I have thought about the question of whether life exists elsewhere in the universe, and I have always framed it as a question we might answer in the future. The tools were not there. The telescopes were not sensitive enough. The planets were not well enough characterized. The theoretical framework was not developed enough. The question was one for the future. And now we are in a situation where we have a specific planet at a specific distance with a specific atmospheric composition that has been measured with a specific telescope that produces a specific chemical signal whose most natural explanation in every known case is biology. We do not know the answer. We are not at 5 sigma. The abiotic alternatives have not been ruled out. But for the first time in history, We have data that could, in principle, be evidence of extraterrestrial life from a specific world that we can point to and name around a specific star that we can see in the sky. That is different from anything that has come before. And I think it deserves to be recognized as different, even as we maintain the scientific caution that the evidence requires. The scientists who made the detection are trying very hard not to say the thing that the data is pointing toward. They are constrained by appropriate scientific caution, by the standards of evidence that have correctly prevented premature claims in the past, by an understandable reluctance to be the scientist who claimed to discover extraterrestrial life and was wrong. But the data is what the data is. And the data says something is making dimethyl sulfide in the atmosphere of a world with liquid water oceans in the habitable zone of a red dwarf star 120 light years from Earth. We do not know what it is. We know what it is on Earth. The most natural explanation for dimethyl sulfide in a planetary atmosphere with liquid water is the same explanation that works on Earth: life. We are not alone. We do not know that yet. But K2-18b is the strongest evidence we have ever found pointing in that direction. And the scientists who found it are trying very hard not to say it. If this changed how you think about the possibility of life in the universe, if K2-18b looks different to you now knowing what James Webb found there, tell me in the comments. Tell me whether you think 3 sigma is enough to take seriously or whether you want to wait for 5 sigma before engaging with the implications. Tell me what confirmation would look like for you and what it would mean for your understanding of our place in the universe. And tell me whether you think the Fermi paradox gets harder or easier to resolve if K2-18b has life. These are the most important questions that science is currently asking. And subscribe if you want to stay at the frontier where the data is arriving and the interpretation is being worked out in real time.